All right, so this first part of this is pretty easy to understand, and then we'll get into these things called ice tables. So that'll be good here. All right, so equilibrium constant. It's K. K is just the generic label for it, K. But really, we write Kc or Kp. Kc would be the equilibrium constant using concentrations, and K sub P would be the equilibrium constant using partial pressures. So let's just do a generic example here. A plus B is in equilibrium with C plus D. If I want you or the book or the AP test or whatever, you're ever asked to write the equilibrium expression, this is how you would do it. You would write K equals, and let's say we're going to use concentration. So technically Kc. I'll do both. I'll use concentration and partial pressure. So how would you solve for this? This is an actual number. If they gave you a reaction at equilibrium, you would have to either figure out the concentrations or they'd have to tell you. And then you would take the concentration of your products, divide by the concentration of reactants. And you would multiply the two together. So you would multiply C times D divided by A times B. You would get one number, and that's called K. That's your equilibrium constant. And that's if it's in concentration, it's Kc. That's just the symbol, Kc. Both Ks mean the same thing. And then if we were using partial pressure, technically you wouldn't have moles per liter. You would have ATM or torr or something. Usually it's ATM, but you'd have the partial pressure of C times the partial pressure of D divided by partial pressure of A times the partial pressure of B. So all I'm trying to show you or teach you right now is what is an equilibrium constant, how do you find it? Of course, we're going to do sample problems, but this is how you set up your equation to figure out equilibrium constants. So you're given a reaction, either they will tell you what the concentrations and partial pressures are, or we're going to figure out how to figure them out in a question. So once you get them, you just do products over reactants, and then that's it. That's how you get the K. The only thing I would like to, I guess, add to this, I should have done it first, I guess, is let's put a little a, little b, little c, and little d in front. Those represent like the coefficients. So if this is a 2 and this is a 3 and that's a 1 and that's a 2, you would raise your reactants and products to that coefficient. So C would be raised to the little c, D raised to the little d, A to the little a, B to the little b. Same thing over there for the partial pressures too. It is confusing with I guess letters here, but we'll do examples. All right. Basically, what do you need to know to find K? It's products over reactants, and you always raise them to their coefficient. We'll do real examples. Actually, they're opposite. And if K is large, the equilibrium, I'm going to word this a couple different ways. If K is large, and I'll give you an example, the number 50. If K is 50, that's a big number. And the way the book actually writes it is, I think the book does this. What is that?
Super greater.
Super greater than 1, right.
Yeah.
So if it's greater or greater than 1. So we kind of use 1. We kind of use 1 as like the tipping point, sort of. If it's way past 1, let's think of the math. If this is way bigger than 1, let's just say 50. The scale gets really like weird, so just stay with me. If this is a pretty big number, that means you have a lot of products and not a lot of reactants. Does that make sense? Like just from the math perspective? And if K is less than 1, really small, let's say it's 0.005, then you're going to have a little bit of products and a lot of reactants. Does that make sense? Okay, so that's important to understand. These come from this. You have to do it experimentally. You have to get pressures or concentration, products divided by reactants. So you just kind of have to know a couple general ideas before we get into the practice problems. This is one of them, how to solve for it. And then this, in general, you need this relationship. You need to remember this. If K is large, equilibrium, how did I word this? I'm already getting confused here. Lies to the right, or lies towards to the products. I know that sounds weird, but that's the terminology. Or we could say favors product formation, or we could write favors the forward reaction. All of those three things mean the exact same thing. Means we're going to the right. We're making more of what's on the right, the products, than what's on the left. Now remember, don't get confused. What's equilibrium mean? The rate is constant. So we may have 10 million moles of products and 2 moles of reactant. So it's way lopsided, but as long as they're changing at the same rate, we can still call it equilibrium. So the amounts of them, the concentration, that does not affect whether it can be at equilibrium or not. So this just tells us, are we making a lot of products, or is there more reactants once it reaches equilibrium? So this only tells us kind of the concept of which one do we have more of. That's basically the whole point of this. Okay, so that's if it's really large, and if it's really small, it's the opposite. Okay, I'll write it down, but it's the exact opposite. So if K is really small, so if K is really small, so a small K, then we favor the reverse reaction. The equilibrium lies to the left, and we favor reactant formation. So I can't stress enough how important it is to remember how to find K and then what it means. If you get a big one, what does that mean? It means we're favoring going to the right, meaning we're making more products. And if we get a small K, we're favoring going to the left, meaning there's going to be more reactants. So if you can get that straight, it makes the practice problems a lot easier. Questions? So I'm just going to kind of give you a quick example here before we get into what I have in the notebook. Let's say, just stay with me here. Let's say we have A and B produces C. Let's say we start with 0.1 mole of each one of these, and I know at equilibrium the K value is 100. So just look up here. Before this reacts, we don't have C, so let's say this is not created yet. So initially you put 0.1 moles of both of these reactants. They react, they reach equilibrium, and the question tells me that's the equilibrium constant. At equilibrium, will we have more or less C than A and B? Don't answer out loud. Based on what we just talked about. We start with 0.1 mole of each one of these. Initially, you're in a flask, you dump them in, okay? Or maybe it's the gas, you pump them in, whatever, they react. It finally reaches equilibrium. That's the value of the equilibrium constant. Based on what we just talked about, would you expect the moles of C to be greater than the moles of the reactants or less than the moles of the reactants? So greater than 0.1 or less than 0.1? What does that number mean is what I'm getting at. That number is really big. Kara, what do you think? Yeah, a lot bigger. So most of these, the 0.1 moles of B, 0.1 moles of A, most of those moles are going to be transferred to this side because that number is very large. If I was to give you a very small K, all right, let's say the K was 0.001, then only a little bit of these are going to actually react and form C when they reach equilibrium. You're going to actually have more reactants left, less products at the end when they reach equilibrium. They are going to react, they are going to form products, but the ratio between them, there's going to be more reactants because that's a really small number because of the math here. So if you have a really small number here on top, a larger number on the bottom, you're going to get a very small K. So that's the kind of stuff I need you to understand conceptually. Otherwise, when we do the math and get into the hard problems, you're going to be lost. So I've repeated myself a few times. Hopefully it's helping. I'll say it one more time. Big K means we're going this way. We're making lots of products, not as many reactants. And then small K, we're We're going this way, lots of reactants, not as many products. Again, you are at equilibrium, so they're changing at the same rate, but the amounts of them will be different. Okay, hopefully you're with me on that. All right, so I'm going to write down, let's see here. I'm going to give you 2 examples. I'm just going to write the reaction on the board. All I want you to do is this. Show me how you would set up the equilibrium expression. That's all I want you to show me is this, how to set it up. So, here we go. And what do we got? Okay, yeah, we'll probably end with this on this period here, this class. Well, that's all right. So here we go. Let's go with 2O3 gas is in equilibrium with 3O2 gas. So there's your first one. Second one. Actually, I'm going to give you 3. 2NO gas plus Cl2 gas is in equilibrium with 2NOCl gas. And then the next one, I'm going to kind of jump ahead because I've already talked to you about this. All right, Live, I'm going to give you 2 more. Just keep on keeping on. Oh, Saved by the Bell. Take a break.